And welcome back to some theories in regression analysis. Right, so we started by looking at some. Let me open the PDF. Some interesting facts about correlation analysis. Okay, and then we said that when you transform the variables linearly, it doesn't affect the correlation coefficient. Alright, and then we also said that the sign of the correlation coefficient is the same as that of the regression slope. Right, so if this regression slope, the sign is positive, then we expect that the correlation coefficient between those two variables would also be negative. Alright, so that is what we looked at. And then we looked at the fact that if you find a correlation between two variables, that does not mean, or it doesn't imply, that there is some causation, or some one of the variables caused the other. Okay, you can't say that. And we looked at the formula for the regression correlation coefficient. Remember, we said that the population parameter is rho and is estimated by R. So the unbiased estimator is what is given. Alright, so simplified version, SXY, which is believed to be the covariance between X and Y, over the sum, or the square root of the sum of the individual variances. Alright, so that is that. Individual standard deviations. Okay, so this is the properties of the Pearson correlation coefficient. So we are saying that the Pearson correlation coefficient has no unit. Okay, has no unit. So we see that it has no unit. There is no unit. So take note, there won't be any unit, because you're kind of trying to divide the same unit on top over same unit down, so you kind of cancel out, so you get a constant which is a weighted average. That constant you get has no unit. Okay, and remember that always R is always between -1 and 1. Okay, R cannot go beyond any of that. So if we are very close to -1, we say that there is a strong negative linear correlation. Okay, so if this is the number line, and then we have a 0 here, and then we have a -1 here, and then we have a +1 here. So if you are very close to this, so you are somewhere here, we say that there's a stronger and a negative, okay, linear relationship between the two variables. Okay, so the more you are going away from -1, alright, then the relationship becomes weak. Okay, so the more you are going close to 0, there is no correlation at all. So when you get to getting close to 0 means that correlation is reducing. Okay, when you begin to go ahead of 0, moving towards 1, then the correlation becomes strong positive the more you move to. So when you are very close to 1, it's a very strong positive linear relationship. Okay, So when you are on 1, you get a 1. That's a perfect positive linear relationship. If on a negative line, you get a perfect negative linear relationship. Okay, so take note. All right, so these are various scatter plots, okay, illustrating the strongness depending on the. So you see that when you saw r is 0, there's no pathing. You can't see where the data points are moving towards, okay. But kind of when you are getting close to a -1, you see that the more when you get 0.5, you can see that they are moving upwards. All right, then in this direction there's a positive 0.5. So when you saw negative 0.7, you see getting close to a -1, you see the pathing is actually being created. So look at negative at 0.9, you see it's almost forming a straight line, okay, and at negative 0.99, which is almost in a line, right? That means the data points are moving upwards. All of them are moving in the same direction, okay. So this is a typical example. We have weight and then some, I think, systolic blood pressure. You want to look at that, the correlation between your weight and your blood pressure, okay. So this is a sketch of that. You see that the sketch look scattered, but you can see that at least they are trying to move in the same direction. With when you are increasing your weight, there is some slight increase in your high blood pressure, okay. So this doesn't really speak a lot, but it kind of give you some pictorial representation of what is actually going on. So when you look at that, you see, because it's moving in this direction, kind of when your weight increases, kind of your blood pressure also try to go up. So if you look at that, you can see that there is some kind of positivity in that data point, okay. So kind of saying there's a positive relationship. All right, so you can just draw this line. This is a line of best fit, which is almost all the time you can get this line from performing a regression model, and you can get that line. It's a linear line. So this so when you did a correlation, you saw that there is a positive correlation, because when you get a positive answer, there is that positive correlation. And remember, this is 0.75, which is kind of strong, okay. So strong positive linear correlation. So remember that in Excel you can run and see the output, okay. You can see your regression output, the multiple regression, R. You can see your R squared. The R squared is what we actually use to measure the efficiency of your regression model. We have the adjusted R squared, standard error, and then the observations, okay. So this can be done in Excel so nicely. All right, so remember the distribution of the correlation coefficient. So this is a standard error of the correlation coefficient. We say that the standard error is given by 1 minus r squared over n minus 2, okay. And we are saying that this follows a t distribution with n minus 2 degrees of freedom. So it means you can use this standard error to create a 95 a certain significant level confidence interval. Try to use this for hypothesis testing and other relevant things. So this is a typical example. You want to test this hypothesis that the row is 0 against the row is not equal to a 0. So it kind of, you are trying to find out whether you got a certain sample estimate R, okay, and you want to see that the population parameter is different from 0 depending on the value that you have at hand from the sample. Okay, so you want to test that hypothesis. So you write down your null and alternative hypothesis and try to compute your t value, which is just R minus rho, and it happens that rho is a 0. So simplifying stuff gives you t as that. Okay, so this will give you a test statistic, and this will be your critical value, and you reject h naught if your test statistic is greater than your critical value. Okay, right. So thank you. We end note 1, which is on correlation. Okay, so you can Google and read more on correlation, then we will be fine. Okay, bye bye.